Hello students, today I would like to talk about topic 3 on formal languages and grammars to give you a little overview of the different grammars and how they correspond to different levels of computation. The first level, the most rudimentary one is the level of regular languages, right? And regular languages and regular languages are generated by what we call regular expressions, right? So to generate regular languages, you just need regular expression, what we call regex. In short, regular expressions have the form, 0 star, 1 star, or you could say 0 0 1 star 0 0, any string that of ones of any number of ones surrounded by 2 0 at the beginning at the end, all these kind of strings. And here let's consider, for the sake of this presentation, that we are always in the alphabet 0 1, okay, just 0 1. 0 1 are called symbols, right? But we also call them terminals. And the reason we use the word terminals is that we're going to introduce with other grammars the notion of variables. So a terminal is actually a symbol that constitutes a string, and it's not a variable, right? So if you notice, all of these are terminals, right? We don't have any variables here. So regular expressions are only defined in terms of terminals and using the operator star if we want to. Sometimes we also potentially use the operator plus, but we don't really need it. So 0 plus means basically at least 1 0, right? While 0 star 1 star could be the empty string, or just 0 or just 1, because star means 0 or more. With plus, if you have 0 plus 1, for instance, it would be at least 1 0 and any number of 0 and a 1. We don't really need this because we could actually express it like that, right? That would be exactly the same thing. But just for to make it easier, we use the plus sign a lot in regular expression. Even when you use like a text editor, you can actually use the plus. So regular expressions generate regular languages. Now that's the first level of languages. We can now go to the next level. So there are things that are regular expressions that regular expressions cannot generate, right? If you want to express, for instance, 0 and 1n, the fact that you have exactly as many zeros as 1 in a string, there is no way to express that with a regular expression, because star always means any number. So 0 and 1n cannot be expressed in regular expression, and actually there is something that some method to prove that this is not a regular expression. There is no way to say I want exactly as many zeros, like for instance 0 0 0 1 1 1. I want as many zeros as 1. You cannot generate that with regular expressions. Regular expressions really correspond to the a very rudimentary lexical analysis, right? So we can call that lexical analysis. It's very, very useful if you're trying to make some change in the code, but just at the lexical level. Like I want to replace all the occurrences of 0 followed by any occurrence of 1, and then return to the line by just stars or something like that, or sharp signs, things like that. Like when you do a search and replace on your editor, a text editor. Now, if you're looking for I want as many zeros as one, or more interestingly, in the case of programs, I want as many open parentheses as I want close parentheses. Okay, so here I'm leaving our regular alphabet, but just for the sake of the syntactic example of programs where you want brackets to be well balanced, right? And you don't want one missing bracket on the right. Well, this you can do that with regular languages. For this, you're going to need to appeal to a larger class of languages called context-free languages. CFL for short. And context-free languages are generated by context-free grammars, right? CFG. And so context-free grammars consist not really in this kind of format, but actually in because that doesn't represent well everything you can do with context-free grammars. Context-free grammars consist always in a variable is formation rules, with and a rule being always on the left a variable, and on the right any number of, sorry, I meant to do a gamma here, any number of any string of terminals and variables. A variable on the right and any string of terminals and on the left, sorry, and on the right any string composed of terminals and non-terminals. So you can have zeros and one along with other variables, right? You always have at the stop a starting variable, always, which is going to be your starting point. So you always have on the top left a starting variable, okay? Usually we call it S. How does this work? Well, you start with S, that's your starting point, and you replace S according to this rule, and then you can use any rule specified in the grammar to generate a valid string, a context-free, in the context-free language, a valid string, as long as the final string has no variable left, right? So so here is an example. We're gonna say, S, typically, SOS1, and of course you can have a variable that appears on the left and on the right. That's perfectly fine. SOS1 and then S sharp, okay? So what can we generate with that? Well, you have to start here, and you need at least a 0 and a 1 to start with. And then you're going to replace the S here either by another 0 and 1, right? So either you push to the left the zeros and ones, and you can repeat that as many times as you want. As many times as you want, until you want to stop and use this terminal symbol, which is not really in our alphabet. So I'm kind of cheating here. I should not use that if I want to stay in this alphabet. And the final symbol is going to be sharp. Now, if I want to stay in this alphabet, I could say, well, let's use, instead of sharp, the empty string, right? I could say empty string here, and I just stop with the empty string. That's also, the empty string is a terminal symbol, even though it's not in the alphabet, right? The empty string is always an available terminal or string by default. So this means that if this is a grammar for the language, grammar G1 for the language L1, that means that this belongs to L1, okay? So now, yes, I can indeed represent 0 and 1 n. That's exactly what I did here. I represented the string that is such that there is exactly as many zeros as one through this grammar. Now I can do much more complex things, of course, with grammars like that. You can actually using context-free grammar not only check that there is as many open parentheses as closed parentheses, just with parentheses, but in actual long text of code. I mean, a series of code. You can actually check that even if they are, even if there are things between the parentheses, that you have this kind of pattern, so that it's valid. This actually kind of analysis, the context-free grammars, allow us to generate, the context-free grammars allow us to generate context-free languages that are basically the languages accepted for a program, for example, at the syntactic level. So here we are going to be talking more about the syntactic analysis. This is the typical first step of a compiler, the syntactic analysis, the context-free languages. That's typical. Now, of course, there are things that a context-free language cannot compute. For instance, 0n, 1n, 2n. The fact that there are as many zeros and as one as there are two in this series, this string, that is not something that can be generated by a context-free grammar. You can generate with a context-free grammar. You can generate 0i, 1j, 2k, such that let's call it L2, such that I equals j or j equals k. So either these two are identical or these two are identical. That is a context-free language. Okay, but this one is not, because here we're requiring I equal j equals k. So this one is actually a context-sensitive language. And with no surprise, a context-sensitive language is generated. Oh, it's actually a plural, so I don't need the S here. It's generated by context-sensitive grammars. What does it mean, context-sensitive? Well, these ones are context-free because the variable on the left can be replaced by what is on the right according to any rule. Yeah, you can use any rule you want at any point, independently of the context around the variable. So here on the left, you always have one variable. Okay. Here I use the same variable, but you could have multiple variables. You can have t, b. So you can have a very complex grammar, but in the end, the variables on the left is the variable on the left is by itself, and of course it doesn't depend on the context, right? So for instance, at some point here in my unfolding of the rules, I'm going to be at 0, 0, S, 1, 1. The step right before this one, and then I replace S. I use the rule 1, I replace S by 0, S1, and I go there. And then I use the rule 2, I replace by empty string, and I'm done. Well, here when I replace S by 0, S1, I'm not looking at what is around S, right? S is by itself on the left side, right? It's always just a variable by itself. It doesn't depend on the context. The fact that there is a 0 and 1 doesn't matter. So in some sense, the machine, if you can think of it as a machine, the grammar that generates that is kind of blind, if context blind. That's why we call it context-free, right? It's context-back. It doesn't look at what's around. So it has a kind of lack of information here because we restrict the left-hand side of the rule to be just one variable. Here we're going to say, no, the left-hand side of the rule can be basically, and that's going to be the definition of a context-sensitive grammar. You're going to have a context to the left-hand side of the rule, alpha, beta, around the variable a. So a is a variable. These are variables or terminals, doesn't matter. And then I'm going to have the same alpha, beta, the same context that surrounds any gamma that is a series of variables and terminals too. The only restriction is gamma cannot be the empty string. It's the only thing. Different from empty string. That's the only thing. But then you can replace pretty much everything you want. You can replace all the Greek letters here by anything you want. The only constraint is this is not empty string and this has to be a variable. So you have at least one variable on the left, at least one. And on the right, you have at least one element here. It cannot be empty. So of course, a context-sensitive language includes context-free languages, right? Because I can rewrite these rules using these. I just get rid of alpha, beta, and that works. But I can do more now. I can do more, and I can basically. We're not going to go through a lot of examples because that would take forever. But now I can say 0, 0, 0, s. So if I have 0, 0, s, I can replace that by 1a0. Okay. I replace this whole string by 1a0. So I should always have my start variable 0s, and then let's say a is going to be a 111, and that's the terminal. So I start with s. I replace s by so this is my context sensitive grammar. I replace s by 0s, and then from 0s I can go. Sorry, that's not the same arrow as this arrow. This is the arrow of the succession of replacements in the rules. So it's what we call a derivation. So let's make sure that there is no confusion. I'm going to use a double thing here. 0s, from 0s I can reuse this one, so I can do 0, 0s. Oh, now I have 2, 0. So now I have 2, 0. I can use that rule, but I can also keep going, right? So I can use, but I can use that rule. So I can now do 1a0, and from 1a0 I can I don't have any other choice than using that rule, so it's going to be 1, 1, 1, 1, 0. Okay, that's a very silly grammar, but that's an example of a context-sensitive grammar. So obviously we can do much more than that with that. We can compute a lot of languages. We can generate, I should say, a lot of languages. Actually, so much that this class of languages is very, very close to the last class of languages. So in short, pretty much all the languages generated by this, the languages generated by these grammars, so the context-sensitive languages, is very close to the class of Turing decidable languages, of all the languages that can be decided by a Turing machine. So it's a very, very large class. And that piece you don't need to look into right now. That's not the crucial part. So another way to describe this description is a bit harsh to grasp because of the alpha beta. There is another equivalent way to define the context-sensitive languages that I like because it's very easy to understand. We can also talk about non-contracting grammars. non-contracting grammars. So non-contracting grammars. Sorry about that. So non-contracting grammars. What does it mean? Well, it means that another way to interpret this is basically put, and here actually I use the non-contracting grammar rules because if you notice there is not the alpha beta, so it was not actually a great example, sorry about that. It's still a legitimate grammars, but it's more from the perspective of a non-contracting grammars. So non-contracting grammar basically only states that the right hand side of the rule has to be at least as large as the left hand side. It cannot be smaller. It's very, I mean, it's very easy to grasp, right? You have a rule like that alpha beta, and you have to make sure that the size of alpha is greater or equal to the size of, is less or equal, sorry about that, to the size of beta. So beta, the right hand side, cannot be of a smaller length than alpha. That's why we say non-contracting. When you use the rule, you cannot contract. And it has to do with the non-empty here. Basically, non-empty, you can interpret that as, okay, you need to at least have a correspondence like one here, and then as you expand here, but it's going to be always exactly the same size. This one is going to be exactly the same size or larger. That's why we say non-contracting grammar. So any non-contracting grammar also generates a context-sensitive languages. So that's a rule we can keep. Here, the context-sensitive languages correspond more to the, we could say, the semantic analysis. When we think in terms of compilers, then the syntactic analysis. It's much more powerful, and you can analyze other features of the code that you cannot analyze here, of course. The last category of languages is the category of basically what we call recursively enumerable languages, or Turing recognizable languages. I don't have any more room on my piece of paper, but recursively, that's a very enumerable languages. That's a very strange name. The reason for that is that here we are in a certain framework, right, of languages and grammars, but as we go larger, now we reached a level of languages that actually has been reached through other theories, right? So here we are in the same consistent theory, but now we are kind of overlapping with other theories that have been developed in parallel or even before these theories. So we kind of have to agree on names. We have to kind of make compromise, right? There are actually several theories that have been like kind of converging on one same large set. There is all these language theories, there is the lambda calculus theories, and there is the Turing machine theories. There is actually also the recursive function theories. And all of them reached almost independently, it's pretty astonishing, the same conclusion that the highest level of computable languages is this one. And because of recursive function theories, the one developed by Gödel, we call that recursively enumerable languages. But because of Turing, we also call that Turing recognizable languages. So there are different names, but just because we reached an area that is common to everybody. While these actually, it's interesting, not all the theories have this level of details of different layers, right? Recursively enumerable languages, super easy. They are generated by unconstrained grammars. unconstrained grammars. Unconstrained grammars, super easy. It's any alpha, arrow, beta. So here the last constraint we had to say alpha needs to be smaller or equal to beta, we just get rid of this constraint. That's why we call it unconstrained grammar. Any rule. And basically these grammars, like this series of rules where you can have any rule with any number of terminals and variables on the left, on the right, in any order you want, this kind of grammar is equivalent to a Turing machine. Okay, so that's basically equivalent to a Turing machine. It has the same computing power in terms of generating languages. But again, that's the part you don't have to worry too much about Turing machines right now. That's not in the program for this course. I just wanted to give you an overview of the different levels of languages, what they mean in relationship to each other, and how they are more and more permissive, right? More and more permissive. First, by going from just pure terminals to introducing the notion of variables in the rules that you can replace. Then by adding the notion of context around variables that can matter when you replace. And then by saying there is no more constraints. You can put any variables, any terminals in any order you want of any length on the left and on the right of the rule. Okay, so that's it. Finally, last point, I'd just like to point out that, of course, I've alluded to that, but all the regular expressions, regular expressions are, of course, also context-free languages, right? And all the context-free languages are also context-sensitive languages. And all the context-sensitive languages are recursively enumerable languages. So that's the end for this little presentation. I hope it helped clarify a little bit the notion of grammars and languages and the relationship between the two. Thank you very much.